All right, today we're going to talk about the predator and prey model, or also known as the Lotka-Volterra model. My name is NOORALDEEN ALDEEB, metric number 2095886.
Okay, my name is HILAM Swami Vivekananda, and metric number 211373.
Hello everyone, my name is REESHI Sadakumar. My metric number is 210913.
All right, so those are the topics we're going to be discussing today. Moving on to the introduction, population fluctuations between predator and prey can be expressed mathematically using systems of ODEs. The Lotka-Volterra can be analytically analyzed or also by using a computer simulation as shown at the end of our presentation to calculate period lengths, critical points, and other practical information to the certainty of the relationship. Therefore, being able to have a prediction of such relationships can be very useful in the biological fields regarding extinction based on predation, or even when it comes to studying excessive coevolution based on population interaction. The ODEs of the predator and prey model. The predator and prey model is a pair of first-order nonlinear differential equations frequently used to describe the dynamics of biological systems in which two species interact. A species is a set of animals or plants in which members have similar characteristics, and one as a predator and the other as a prey. The populations change through time according to the pair of equations shown below. So the predator is the animal that kills and hunts for food, and the prey is the animal that gets killed or hunted for food. Here is the two equations as a model, and those are a couple of pointers about it. Regarding this model, the primary concerns on survival for different species is what derives theories like natural selection and evolution or co-evolution. Further history, in 1910, the Lotka-Volterra model, or the predator-prey model, was first proposed by Alfred J. Lotka. And in 1925, Lotka used the equations to analyze predator-prey interactions for his book, Biomathematics. And in the 1930s, Vito Volterra proposed a differential equation model to explain the observed increase in predator fish and therefore the decrease in the prey fish. Because Volterra was working with D. Ancona, who noticed the percentage of predator fish caught in the Adriatic Sea had increased during the years of World War I, which made him very curious because the fishing was supposed to be decreased around that time. So Volterra developed his model individually using Lotka's theory to explain the Ancona's observation. In the 1980s, an alternative to the Lotka-Volterra was the ratio-dependent or the Arditi-Grisenberg model. The Lotka-Volterra model assumes that the prey consumption rate by a predator is directly proportional to a prey abundance. This means that for a predator to eat, its food source is only limited to the prey amount they have in the environment. This can be imagined as a fox and a rabbit. The rabbits are born to their death causes are predation or inherent, and the foxes are born where the high predation rate positively affects their birth. So therefore, this shows us that they can both be justified in terms of each other. So in one word, the quantity of foxes has a negative effect on the rabbits, and the quantity of rabbits has a positive effect on the quantity of foxes. Next slide. The first paragraph basically says that the mathematical abilities comes and provides a simulated outcome of the future, which can, as said, potentially help in avoiding such tragedies as extinction, co-evolution, and etc. Many species share the same ecosystem, which means they live together, and their mutualism occurs, which means that let's take in mind oxpeckers and zebras. Oxpeckers benefit from having a ready food source, which is the bugs on the zebras' backs, and the zebras benefit from the bugs having removed. However, what is widely known to be the most common source of interaction here are predation or competition. Last thing is co-evolution, which turns into a biological competition between predators and prey. This means that basically preys over the time develop adaptations in order to survive more, and then the smarter or more clever predators develop higher adaptations, and it just keeps going on and on for both species. That's it from me. Let Hilam take over.
Thank you, ALDEEB. Let's start with intuitive approach. Let's assume that you're observing the rabbit population and fox population in an area. And by common sense and observation, you would know that fox aren't rabbits, meaning the fox is a predator and rabbit is a prey in the area. Without using any math and just using your intuition, think of that. What would happen if the number of fox would increase in the area? You may easily think that number of rabbit will decrease because more and more rabbit will be killed by the fox. It's easy. Then will all the rabbit will be eaten by the fox and they will completely disappear? The answer to the question is not easy. The answer can be maybe yes or maybe no. The answer would be depend on the population changes of fox and how fast the fox is away the rabbit, and etc. To get the answer to this kind of tricky question, you need to use mathematical modeling and understand the exact relationship between two populations. Again, only using your intuition, think of that what will happen when the birth of rabbit increases and the number of rabbit increases. You may easily guess the number of fox will be increased as well as because they got more food easily. Then, will this situation goes forever? Will fox hunt rabbit such easily forever? Probably not, because fox hunt rabbit more easily and the number of fox increases. At some point, the number of rabbit may decrease since many rabbits are hunted. And decreasing number of rabbit means decreasing the food for fox, and eventually the number of fox will be decreasing as well. Now, you may roughly understand the interrelationship between the rabbit population and fox population. If I ask you about exact when the rabbit population will grow and shrink, or exactly when the fox population will grow and shrink, you cannot answer this question without exact mathematical modeling for those population changes. In the section, we'll derive a very basic model of this equation, changes using the differential equation. Let's think about the rule for the population changes of the rabbit. It can be described as follows. Delta P or delta T equal to RP, where R denotes the rate of growth, and this might be beginning of the population model. So what are the different natural events that can inhibit the population? The natural interaction of the rabbit population with the predatory fox population would be logically next step, and because the rabbit is consumed by the fox predation or the kill rate. So a new variable K must be introduced, and this new rabbit fox population model variables introduced the following equation, which is delta P over delta T equal to RP minus K. So although it is simple, this equation illustrates a well-developed population model. In order for this model to be accurate and more variables such as human involvement, temperature changes, restricted food supplies, and natural disaster, and alternative predator are neglected. So we have to make some assumption, which is the predator is completely dependent on the victim for the sustenance, and prey species have plenty of food, except for the predator species under investigation, and the prey is not threatened. To solve the predator model, we want to use the combination of first-order nonlinear differential equation to explain the population dynamics of the biological system in which two species interact. One is the population of the rabbit grows at a proportional rate to existing number in absence of fox. So when is that? Delta y or delta x equal to ax when the y is 0 and a is more than 0. This results in increase of rabbit population. In absence of rabbit, the fox die out. So dy dx equal to negative dy, and x is to 0, and d is more than 0. This causes decreases in fox population. The product of their populations determine the number of interaction between the species. Each encounter has a tendency to enhance the y while decreasing x. As a result, x growth rate content in term of fox form of bxy, and y's growth rate includes a term cxy, where b, d are positive, and t has no effect on the parameters, and a, b, c, d are parameters. And this assumption will lead to this equation, which is delta x or delta t equal to ax plus bxy equal to x bracket a plus by bracket, and dy dt equal to dy plus cxy equal to y bracket d plus cx. And the variable a, b, c, d are all positive, where AD are being growth constant, and the BC are being measure of their interaction effect. The term T must be removed from the equation in order to get the systems part, which I've shown the equation below. Okay, we come to the analyzing the differential equation. So before that, I've shown the equation. So now we are substituting the variable data, which I get from the actual data, which is A equal to 0.5 and B equal to 0.03 and C equal to 0.8 and D equal to 0.05. So this is a sample equation, and this sample equation is a genuine data. So one of the most crucial metrics in the graph is average periodic oscillation by analyzing the same position in the consecutive phase and estimating the time interval between them. So the periodic oscillation may be detected in the fashions the peaks of the curves are frequently used. So figure 5, this figure shows the average periodic oscillation for the rabbits and foxes in 10-year fluctuation, supported by more research and subjected. And this is interesting to compare this graph of the actual data, the genuine data line graph for the predator prey cycle chart. And this graph is made by the equation before I showed using the Microsoft Excel. And these two graphs are compared. It is evident that two graphs overall form, shape, and character are extremely similar, but not identical. But each graph shows the 10-year periodic oscillation with the comparable population maximums. And this graph comparison, in addition to being instrumental and useful, and clearly demonstrates some of the biological model's flaws. And no mathematical model will be accurate to reality, even it is usually correct. In this form of mathematics, it will be any percentage of error connected with judging the difference between the theoretical and analytic facts. So that's all for me. Thank you.
Thank you, Hilam. So now we're presenting about the examples. So now have made two equations here. So the first one, as you can see, dx over dt, we have 0.5x minus 0.004x squared minus 0.001xy, and dy over dt 0.4y minus 0.001y squared minus 0.002xy. So the question given here is determine whether the system represents a system of cooperation, competition, or prey-predator. So now you can see have here stated that x and y, x is fish population and y is bear population. So how to determine whether the system is cooperation, competition, or prey-predator? First, we're going to see the interaction term in both equation. So now, right now, the both equation have negative interaction term. The interaction term we only can notice when x and y term are together. So now both equation have negative. That means this is the competition system. So what happens? One equation have a one positive interaction term and while other have negative. We call it as prey-predator system, where the positive sign interaction term we call it as predator, another one we call it as prey. If both interaction terms are positive, then we call it as cooperation. So we already got the answer. The answer is competition, since the both interaction term on both equation are negative. Let's move on. So now have made the both equation into the equilibrium state by factorizing them using the lowest term, which is x power to 1 and y power to 1, and we are able to get this. So when we separate all these, we're going to get 4 cases of equilibrium state. So we have the first case, second case, third case, and the fourth case. So the first case, when you solve this, you're going to get x equals to 0 and y equals to 0. For the second case, have converted into the most simplest way simultaneous equation in order to solve and to get the x value and y value. We got x equals to 50 and y equals to 300. Moving on to the third case, when you solve this, you're going to get x equals to 0 and y equals to 400. And the final one, we're going to get x equals to 125 and y equals to 0. So after solving all this, we're going to get four cases of answers. So the first case, we're going to get x equals 0, y equals to 0. Since the both population does not exist, therefore we call it as zero population. Second case, we got 50 and 300, and we call it as stable population. Even though the numbers are different between the x and y, but both population have a certain amount of numbers, so we call it as stable population. Moving on to the third case, we get x equals 0 and y equals to 400. But in this case, we call it a stable y population. It is because the x is 0, that means does not exist, and 400 is a stable number. Therefore, we call it as stable y population. And the final one, we call it as stable x population, because x is 125 and y is 0. So small. So here, in order to make our prey-predator model even more easy to understand, I've made a Python code here, and I've listed all the Python codes. So once we run it, we're going to get the model. So these are the model. So I've made two different perspectives, one for fish and bear, but we can use this both model in order to explain at one time. So as you can see, as time increases, and the population of fish begin to decrease. This is because when the time increases, the population of bear begins to increase. So the fish starts to decrease and the bear starts to increase. So this is because the bear starts to hunt the fish population, and the fish begins to decrease, and the bear obtain food from the prey, which is the fish, and the population begin to increase. But when you see at one point, the population of the fish approximate to 0, and we can notice that the bear population also begin to decrease. So from here we can understand that even when the prey starts to decrease at one point, predator also starts to decrease. So the most important thing is that predator need prey, and prey population is depend on the predator's population also. So this is what we call prey and predator model, and that's all from me. I would like to give to Adi for the conclusion.
Thank you very much. Further conclusions, we want to say that models help identify factors that stabilize and destabilize prey-predator interactions. Stabilizing factors are like prey self-limitation, prey refugee, spatial heterogeneity, and predator territorial. And destabilizing factors are predator more efficient and time lags. Information gained as a result from carrying out the Lotka-Volterra model would be very useful to biologists and whoever is studying population, because it can help them prevent such stuff like extinction or co-evolution, and also can show the specialists where the years and seasons it may happen. On another side, co-evolution studies like means of survival and adaptation to competition would be impacted positively by this data, whereas it could determine the number of cycles which is required for each species to develop new means and adaptations. Thank you very much for listening to us, and hopefully we didn't take much of your time.